Let me get the.
Not actual diamonds. If I had real diamonds, I wouldn't be one professional space.
I'm not worried about Brandon. Brandon can hold his own.
And they laughed with me and I was like, no, but like in all seriousness.
He gives them crap too, so
I'm like,
you just don't ever hear him
hands
speak.
to do it. Let me see the kid, he's just.
Around y'all, he had to kind of learn to defend himself.
What I think, like you idiot.
I think he's fine. Right, Brandon?
Oh, now we not talk.
It was good though.
Yeah.
Good experience.
I know. He just says dang it now.
Yeah, we don't have anything for you. We're not.
Damn.
Yeah, it is real, it's way different than being a freshman. Like the.
Y'all, you don't know the torment he
Like levels and the round
says to me.
Still have like 6.
You what?
Yeah, no.
No.
Looked it up,
One
it
of
was
these.
like.
You said that's
Yeah,
so
I
motto.
know.
Just, oh well. Asked me the other day, he goes,
Yeah.
would you rather kill bear or hack off your leg?
Technology. Virtual, you can like.
Valid
virtual
question.
reality.
I mean, it depends on the circumstance. What do you have on you at the moment? Like, do you stand a chance against the bear?
No, would you rather kill bear as in my dog?
Oh, I thought you meant a bear.
No.
My pet dog.
Iowa, Colorado, UT Helton, Houston.
Where did she pay? Off my
How
leg.
much do you like your dog?
I said I'd hack off my leg.
They're like.
I love my dog. I would never kill bear.
Texas. Why
Would you rather kill bear? I'm not, and that's literally what I said. He goes, would you rather kill bear? And he sat there and thought for like a good minute. I'm like, I'm not killing bear. It's just a hypothetical question.
Question, would you rather kill bear or kill
I've never been.
Brandon.
Yeah, some more.
Brandon for making me answer these stupid questions.
Maybe hopefully if Texas is certain.
Yeah, I
Great.
agree.
But she doesn't look.
All right.
She was like.
Measuring pressure.
Now you know.
really easy resume.
Okay.
Perfect, so now it's on.
If we're on a solution that solves everything organic and we'll leave everything inorganic.
Nope, I would just kill someone with an icicle.
That's what I've
I
always thought.
just started the recording again.
I've literally always thought that.
I said I would I'd kill someone with an icicle because then it melts.
Are you gonna put toilet paper on the people who made it?
Just have to restart this whole thing all over again.
Well, I'm gonna leave her admissions for the world.
You wanna try that out? I'll
That'd be
go
hard
first
to
and
do.
There's so,
That's other schools.
something has damaged you over the course of your education.
Yeah, I fear it.
Now, do you think do these?
I'm scared.
Oh my god.
Okay,
My mom asked me if I asked him to go.
measure pressure.
What she was saying there.
You still not started.
I've got to get through this. The intrusive thoughts are
So, like,
really flowing right now.
Pause the recording, Sam.
Pause the recording and
From
say.
this weekend.
Nope.
Pause the podcast.
Nope.
I
What's
don't know
the
what
point?
you're saying, now that you say that.
Oh. I gotta say hi to everybody who's listening.
I hope I look you lose.
Hello.
Or this.
I already know Hannah listens to this, so she told me she can hear me talking.
That's the voice of our resident murderer.
You're fine. Stop being mean to me. I could never. I can't even kill an animal. I would never even.
So here we have, technically, I think this is called a manometer, but it just, like, I'm looking through the textbook and it goes, let's take a look at the manometer. And
Manometers.
it's not. Let's go back to the barometer. But
Manometer.
Mercury's pretty good too.
basically, it's one of these devices where you have a fluid in it, either the red alcohol fluid or the mercury. One side is open to the atmosphere, the other side will have pressure applied to it. You could measure the gas pressure. So the whole point is we're getting to a gauge pressure. And as you notice, and what are those three symbols again? There you go. Still waiting for someone to say T.
So you say what?
What's that?
Yep. Rho is the density of the fluid inside the meter. Okay, so remember we have our basic equation.
So if you use this thing tomorrow.
So let's say we have a point A, and then we have B and C. So you can see the difference between point C and point A. Nope, nope. Pressure C. So, and of course, that difference in the pressure, between the side that's open to the atmosphere and the side that where you have gas applied, that is going to be your rho GD, or if you remember from your chemistry textbook, that it was rho GH, same thing. And so that difference in pressure is your gauge pressure.
Sometimes I read gauge as GOG.
Because you were the one who last week told me you didn't know how to use your textbook.
We already had it.
And that's a conversation I will never forget in the textbook. I don't know how to use the textbook.
I said I don't know how to read.
You're the first person and probably the only one who will ever say that. And I know you're kidding,
Told him
because I
didn't
know
how
you're trying to get
read.
out of having to do it.
Yeah, I actually don't know how to read.
What was that freshman year? Shall we bring back the references to the nun?
No.
I forgot about that. That was funny.
No, they read that correct.
Okay. Then, of course, I make my horrible dad joke. I couldn't resist. We have a mercury-filled manometer connected to a container of gas. The height of the mercury column on the side connected to the gas is 22 centimeters, measured from the bottom. What is the height of the mercury column on the open side if the gauge pressure is measured at 13.3 kilopascals? Okay, so. It's that. Oh, God. Cancel out omnibus.
Are you laughing at your own meme?
No, I'm laughing at the math joke.
Oh, the man plus the bet.
Which now I'm making this part of your homework. You have to go home and tell your dad your addition to the joke.
No. I don't really want to talk to my dad.
Why do you think that was about you?
I'll talk to your dad.
Yeah.
I'll touch you.
That's joke a little bit.
Give you more physical knowledge.
Really good.
Dude, that makes me really sad. I've been making jokes for years and you're like, this is probably the best one you've ever made.
I don't know, it's like,
Like-
really good.
How bad has it been?
Like, pretty good, but like, this one's good though.
Okay, so let's think about what happens here.
No, when you warm up, you'd be moving when you hear another person.
So let's start with saying,
Yeah, with the floor.
before any pressure is applied,
There's 3 in a row for all 3 classes.
we have our fluids, the fluid in there is at equal levels.
I do think it's nice that they do.
And so then pressure is applied. Forcing the fluid to move. Okay, so then of course the side where the fluid is higher is open to the atmosphere. Okay, so to actually label this in a way that will make more sense, let's go ahead and remove these. So what we're going to do is we're going to have a height. Height A. So because this is part A. So the subscript A that I'm about to use is because we're in part A. So that's that distance A that we're talking about. That's going to be that change. Then we're going to have an additional distance down to the very bottom of the meter. And then this whole thing here. We'll call that the height of part A. Okay, so the gauge pressure. Will tell us rho GD.
Small school. Regions, like usually two teams that would make it to like even just a Sweet 16 would be in the top four.
And so then from here, we plug in our numbers.
Oh, never mind.
And we're going to get a distance of 10 centimeters. So then it asks, what is the height of the mercury column after we find this? How do we figure out the height of that mercury column? Let's relabel this a little bit to make it maybe make it easier to answer this question. The distance has to go from there. Go from where it was, but we're measuring to the very bottom.
So you need.
Well, okay, I'll go ahead and do this to make it easier to see how we solve the problem.
Or something like that.
Look at it like that.
So the whole DA would be 2 times what we just got?
No, we're just gonna call that D, I'm just relabeling it so we can see how to actually solve this problem. Because we get that distance. That distance between the two, we're gonna look at the distances, between the two. Ends of the fluid.
Oh, yeah. Okay.
So what do I have to add to it?
A,
Yeah, which is what?
22.
There you go.
So, okay, DA does equal the distance between the two fluids.
Yeah, right.
Okay.
It's not that far.
Okay. So that's part A. Now, I want you to spend a few minutes working on part B because this one is a logic test. I want to see if you can get it.
Doesn't your brain have to work for that? Sorry.
I mean, it is a Friday and break is next week and who's going to be here on Monday? Really?
Lab.
We're all taken off.
lab.
Huh.
This is the only class I have Monday, so like I'll just.
Hey, gang.
Some of the teachers are being really cool and not making kids come to class Monday or Tuesday.
I don't know if you, I don't know if you had realized, I'm a physicist. I've never been cool. Besides, we've got to get into sound, so.
Buildings. I mean, do we have to?
Well, I was saying that the people who take the MCAT are gonna have to know sound, but then I was told today, nobody in here is taking the MCAT.
Really? Really?
You mean this year, no one's taking it?
No, it's a joke, guys. I told him I wasn't taking it.
But you told me no one was taking it.
I said, nope, none of us are taking it.
So do you just have to do double?
It's a little more difficult than that.
For carnivals, Thursday. Today.
Yeah, we just straight up solve it again.
See, now you have to do.
We could double, it's double what we had before. Yeah.
You would think so. It's not. Think of it this way. One side goes down, the other side goes up. But the total volume of the mercury doesn't change.
Okay.
I have no idea.
You don't see anyone.
It's just, maybe it's our
Why?
position double.
I'm having a hard time with my diagrams today.
She's been playing for like.
Like the position, like the.
She's like very young. Maybe she switched schools too. I don't know.
Hey, saliva. I don't even know what this
Let's see.
Like this. Starting where. I throw up the number.
Okay, well, okay, so that's the first part. But then there's like a logic after that.
That's what I'm saying.
So let me draw a more in-depth diagram, okay?
No. There we go.
Yeah, but she was so tall too.
This is right there.
But she was really
Couple
good.
inches on.
She was really good. I don't know. I didn't know. Oh, I didn't hear too much about it, but I knew she could. These switches.
It's horrible, but it worked. Okay, so. We can say. Both fluids start there, okay? Or well, both sides start there, same fluid.
Yeah, she is. That's what it makes.
Then you put the first pressure in,
I don't like trying these.
go there. You go there. Then. Gauge pressure doubles, so that means that this side now is going to get pushed down further. This side will go up further. Okay, so
I just don't understand.
that's that new distance for part B. That's that distance for part A. There's your 22 centimeters. That,
Well, I guess all of this.
there's an accurate diagram. Can you use all of those different measurements to figure this out?
I mean, when I reported it, I got 42.
The high side,
Yeah. I see.
it's 37.
It's 37?
Mhm.
Shame.
I know.
I know, but the way you're solving it, that's like the straightforward intuitive part. But there's a little bit more thinking that goes into this. So yes, 42 is a very intuitive answer. This is one of the problems like this is one of the reasons that people don't like fluids.
So there's something.
Yeah, it's the drawing.
Two was 37.
Okay, so let's just kind of start looking at this. What if we said, so we have that on the left side, we have that height that for part A, like the fluid, the mercury gets pushed down to, we put more pressure and it gets pushed down to B, okay? So we can say that difference, A minus B, is going to be the same difference as those two heights. Now we know that. Look, this is how you solve it.
It's the number 7 and number 6.
Okay, so our numbers from part one. This 54 here is key to solving the problem. Okay. Now, HB, what can we replace that with?
B plus D.
Mm-hmm.
That's what killed you.
That's like, why it sounds so.
And since for some reason I can't get my brain to work for these figures today, there is a figure in the textbook that'll explain it better. This is how you solve it though. Now, we need to figure out what dB is. You did that,
Oh, is that the 42?
not 42. So let's do the P.
She's like, I did.
Oh, 20?
Yes. It's the same density, same G, except the pressure is now 26,600 pascals, because it was double the pressure. The first one was 13,300 pascals, this one's 26,600 pascals. So that means dB is going to be 20 centimeters. Okay? So now, that means we have two B plus centimeters. 4 centimeters. 2B is now 34 centimeters. B is 17 centimeters. But
You have to put it back.
HB is B plus DB, so 17. Now, can you see the logic of it?
I guess.
Go back through it, compare it to diagrams in the chapter. But this right here, this is kind of like your real first look into why fluids tend to throw people for a loop.
Because it causes your brain.
Yeah, a lot of the way fluids react is not intuitive. Okay. The buoyant force.
Is he fighting a bear?
Yeah,
Oh, no, hugging a bear.
with
No.
a fish.
no, fighting a bear for a fish. That's actually a video. You should look it up. That bear does karate.
Is it AI?
It's not AI.
Oh, no, like crazy videos or like people like, they're like, I don't believe it because it's all AI, you know?
Yeah, but this was before AI. So.
Yeah, but some people don't know that.
True. Okay. Buoyant force. Can anyone give me an idea of what buoyant force is?
Pushing you up.
Yeah, so you go down in a fluid, you have a force pushing you back up. That's why you weigh less in a fluid.
It's when it's like when your density is less than what you're displacing.
Yeah. So eventually, I mean, you get to the point where if you're floating, you've displaced an equal amount, an equal volume of fluid to your volume, but buoyant force doesn't necessarily have to mean you're floating either. You can still sink all the way to the bottom, you just weigh less.
Perfect. For real. Skinny.
Just us.
Okay, so let's say in here. Not great, but you get the point. Now, the top and bottom of the cube of a surface area A. That is going to be, so when we were looking at water pressure based off, and now this is an actual object in the fluid instead of just imagining like this little canister of fluid inside a fluid. But still, we're looking at that distance because we know that pressure is going to change a minute amount from the top of that to the bottom of that. And we know that there is there's a gravitational force. Now, on each surface, now first off, again, why am I only worried about these two forces of the fluid on the top and the bottom?
The sides cancel.
Right, the sides cancel each other out. Okay, so. Now we know due to the fact that pressure changes, force 2 will be greater than force 1. And then the definition of your buoyant force. Force one plus your force two equals your buoyant force. Because when you think about it then, your buoyant force, so your force one is a negative P1 times that surface area A. Your force two is a positive P2 surface area A. That's delta P, so delta P equals what? Yep, but what does it equal? It's your gauge pressure, so it's what?
GD.
There you go. Your buoyant force is now going to be rho GD times A or rho G B of your object. Why did I change that D times A to volume?
D times the A equals volume.
Yeah, so the length of the cube multiplied by that surface area, that's going to give you your volume. Or your cube, length times width times height. Here's how you expected to use more room.
Add page.
There. But Archimedes' principle is a very important thing to keep in mind. So fluid exerts an upward buoyant force on a submerged object equal in magnitude to the weight of the volume of the fluid displaced by the object. So that's why, for example, you ever seen the bottom of like a tanker ship? Has that big like hot dog shaped structure?
Yes.
Just because it's trying to displace more water, it's trying to provide a larger surface area so that more of the ship can stay above water. Okay, net force due to gravity and buoyancy. We're just gonna put this thing right up on the surface. Some of it's submerged, some of it's not, it's floating. Mass times gravity. Buoyant force. Some of your forces, we're going to call that Y. Buoyant force. Plus mass times gravity. Now, you need to take a couple of things into account. We're just going to call this your object, okay? So, mass of your object times gravity is going to be the density of the object times the volume of the object times gravity. That makes sense. Density times volume is mass. Buoyant force is going to be the density of the fluid, volume of the fluid times gravity, or that equal mass that's displaced, rho times V. The mass of the fluid that's displaced in order to cause the buoyancy. So that means our sum of forces is just forces in the y direction. Remember, F is fluid, O is object. Now, there's a little bit of difference. What do you think changes about that equation if the object is completely submerged? Not wait.
Sorry.
Only one term in there is really going, there's something in there that's going to become equal. What do you think becomes equal if the object is fully submerged? What?
Pressure.
Not pressure.
If it's.
If the object is fully submerged, it displaces an equal what? Volume. Who said it first? Say it louder. Okay, so the equation then would change. That. And so we can actually use this sum of forces to end up with a topic, an idea called specific gravity. Now, this one you've heard a lot in chemistry, maybe biology classes, specific gravity. Ratio of a substance density to the density of water at 3.98 degrees Celsius. And of course, the reason we use that temperature is because that's where the density of water is at a maximum.
Eva loves cookies.
I know.
So we're looking at a partially submerged regime here. So that means your and when you solve this, you can get the fraction of your volumes. Gives you the ratio of your densities of your object to your fluid, which ends up leading you to this ratio of the density of whatever substance is in the fluid to the density of water. And so that would give you the specific gravity of whatever substance you're trying to figure out. This one's fun.
Minneapolis.
Yeah.
Okay, so we'll finish up a few problems on Monday and then finish the chapter. That means in our last week, we're gonna head on into sound. But for some reason, I couldn't get my brain to latch on to the figures today. Compared to the figures in the chapter for measuring pressure. But just make sure you go through like how you actually solve that, because again, the answer is not intuitive when it comes to fluids.